Okay, so we're looking at this lesson here. So the main difference between today's lesson and what we did last class is that we're not going to be taking rates of change with respect to diameter, with respect to radius, with respect to surface area. All of our rates of change are going to be with respect to time. Right, so we're actually looking at a speed at which something is changing or a velocity at which something is changing. So they're going to be similar in terms of the same type of setup and same type of solution, but now we're looking at it as something is actually physically changing. How fast is it changing? So it's a rate of change with respect to time. Right, so I tried to, I'll give you a little bit of disclaimer that these are relatively harder questions than what you saw last class, and this is one of the harder units. Because there's a lot of application. So that's why I put in today's lesson, which is practice. Next class's lesson, when I see you next week, is also practice, and we're not really learning anything new. It's just we're going to be doing as many types of these problems as possible to be exposed to as much of them as possible, and so that we start to kind of recognize, oh, okay, I've seen a question like this, I've seen a question like this, I've seen a question like this, so that we're hopefully confident with it. So I tried to start it off with something that's easy to visualize. So we have that a pebble is thrown into a pond, and you get that a circular ripple is created. And that's kind of obvious, right? You've all hopefully done that. Or if you have a drop that goes into a pool of water, it obviously makes these ripples. They won't be perfect circles, but relatively perfect concentric circles. They say when the radius of the circle is 3 centimeters, so when that ripple reaches a radius of 3 centimeters, they're saying that the radius is growing at a rate of 1 centimeter per second. So they're saying at that instant, when the radius is 3 centimeters, the speed or the velocity or whatever you will, the rate of change of the radius is 1 centimeter per second. What we want to find is the area at which, the rate at which the area is growing. So I'm going to try to get you guys into the habit of always putting in, okay, what do we know? What do we want? And sometimes we're going to have things that don't change, and we're going to just remind ourselves of that. So here we're going to have that we know that the radius is growing at a rate of 1 centimeter per second. So how we're going to put that in is we're going to label that, okay, well, we know that the rate of change of the radius with respect to time is 1. Right? So that's what that dr dt represents, really. It's the derivative of the rate of change, or of the radius rather, is dr dt with respect to time. So we know that. But we know this when it is specifically at a radius, that this happens at a radius of 3 centimeters. Okay? What we want to know, what the question is asking, is at what rate is the area growing in this instance? So we are looking for what is the rate of change of the area with respect to time. That's what we want to figure out. Okay, before I move on, are we good with how I set this all up, or how I've started to set it up? Yes, Stephanie. It means that the radius is changing at that instant at 1 centimeter per second. So at that instant, the radius is growing. So think of it as a speed, right? So it's moving, it's getting bigger at a rate of 1 centimeter per second. Okay? So in here, we'll put in all of our let statements. So we'll say, let's let A, R, and T represent the area, radius, and time, respectively. Okay, so now that I kind of know what I have, what I need, now I have to come up with some formula. Nick and Phil, can you guys pay attention? Put your laptop away, please. I have to come up with some equation that relates these two things. And sometimes it's going to be really obvious, and sometimes that's where it becomes hard, is not knowing, okay, what's the equation that relates these things? So this one, we're talking about area of a circle, and we're talking about radius. So similar to what we were doing last class, well, our relationship between the two is that area is equal to pi r squared. Right? Area of a circle is equal to pi r squared. Okay, so again, not so new yet. What becomes new is when we go and try to take the derivative of this, we're not taking it with respect to r, we're not taking it with respect to a, we're taking it with respect to time. So the derivative of the left-hand side is going to be, okay, dA dt, so the rate of change of the area with respect to time, is equal to, okay, pi, I don't worry about it, but now the derivative of r squared with respect to time, this is where you have to use your chain rule. So it's going to be, okay, well, what's the derivative of r squared? That's 2r. That's your outside function. And then what's the derivative of r with respect to time? That's dr dt. Right, so what you're doing there is you are applying the chain rule. Okay, but then you end up with this dr dt, which actually represents something. It's not as abstract as it was before. It represents, okay, the rate of change of the radius with respect to time. Yes, Lila?
Why is it not dr dt?
Because in the question, and this is where we have to be careful, it wants to know at what rate is the area growing, and because they gave us the rate of change for the radius in centimeters per second, we're going to be consistent with that, and it's going to be how fast is the area growing in terms of centimeters per second as well.
But it cancels to 1.
No, because it's not the same thing anymore, right? Last class it did because we weren't actually we were taking the derivative of r with respect to r, right? So it was with respect to the same unit, so it did cancel, but now it's not going to cancel anymore. And that's what I was trying to get across last class, is that we're getting to questions where they don't cancel and they actually represent something, and it's important that we include them in. Yes? Okay. So now fill in what we know, right? We kind of labeled that out. Okay, pi is just a constant. 2 times, okay, radius, we know that at this instant, it is 3, right? So we'll put that in. So pi times 2 times 3. And dr dt, they tell us that as well. They tell us that that is a rate of 1. Right? So I haven't put the units in, but they all have their own units. So now we're left with, okay, the rate of change of the area with respect to time is 6 pi. So at that instant, when the radius is 3, the rate of change of the area with respect to radius, with respect to its radius, is 6 pi. What are my units going to be? Good, centimeters squared per second. So we're looking, okay, well, it's dA, which is centimeters squared. It's dt, which is seconds. And this is when, this is only at the instant when the radius is equal to 3. Yes, Anthony?
Why do we define the derivative?
Because that's technically what this means, right? Here, this question here, when it says rate at which the area is growing, it's another way of saying find the rate of change. Rate of change is a derivative. Okay?
We're never going to see ripples the same way. We're going to be like,
Sorry.
Rate of change.
Okay, I'm going to actually skip the second one because it is literally identical to the first one. I just want to make sure that we can kind of go through enough questions. If we do have time or if we want to go back to it, we can, but it's literally the same thing where you have something that is a circle that is essentially it's a disk that is being melted, so it is growing as well. So it's the same exact type of question, just the numbers are different. So I'm going to skip it for now, and I'm going to go to question number 3. Are you guys done in question 1? Did you copy it all down?
Yeah.
Okay. So number 3. A little bit different. You have now a cylindrical tank that has a radius of 3 meters and a depth of 10 meters. So even for me, I think it's always good practice to draw this out, because if not, I get confused, and you might be good enough to visualize it in your head. I'm not, so I'm going to draw it. All right, so a cylindrical tank looks something roughly like this. Oh no, come on, work.